So can you see it?
Yeah, we can see it.
Yeah, perfect.
Do you see also the hand?
Yes.
Yeah.
Okay, so I can try and use it. So, okay, 29. Okay, so let me start. First of all, I want to thank Monica and Tanji for holding on all the same by organizing this workshop despite current difficult situation we are all in, for inviting me and for giving me the chance to share some of my recent activities with you. So I'm going to talk about a joint project with Lorenzo Lampariello from Università di Roma 3 and Simone Sagratella from Sapienza Università di Roma. Actually, it is a very, very recent project, so our results are somehow preliminary, even though we have a first paper out. And so since it is preliminary work, your feedback will be particularly welcome. So our project focuses on hierarchical programming, hierarchical optimization. So an optimization problem where the feasible region is implicitly given as the solution of another lower level problem. And for the time being, we focus on this kind of problem here. So the upper level is an optimization problem. We wish to minimize a function f over the solution set of a variational inequality. So that the lower level is a variational inequality. And please notice that the case we are considering is such that the variational inequality is not parametric with respect to the upper level. So it does not depend on some parameter which is which appears in the objective function f. That is the more general case that is considered, but we focused on this one for the time being. And so first remark, the lower level is defined by infinitely many and probably infinitely uncountably many inequality constraints when y is such, so that actually this is nothing else than a semi-infinite program, a semi-infinite optimization problem. And indeed, our interest in this problem arises, let's say, from some situations that are modeled by this format. The most common one is that actually what you're doing is, for instance, selecting among multiple solutions of the variational inequality. If the variational inequality represents, let's say, a non-cooperative Nash game, you are doing nothing else than selecting according to some criteria one Nash equilibrium. Or in a slightly different situation, this problem here is also generally the objective function of a leader or a pessimistic leader in Stackelberg games, so that the leader has to evaluate the optimal solution of this problem as the worst thing that can happen to him if he chooses a particular strategy. So this is just the objective function. And moreover, this format covers also some another situation which is called simple bilevel programming, where the lower level is an optimization problem. It has received a lot of attention recently, and there are some interesting results. And indeed, this is covered when you are considering that the lower level is, let's say, convex, no-smooth optimization problem in such a way that optimality can be rephrased into first-order optimality condition, which are actually variational inequality, this one here. So this is the problem at hand, but actually we did not focus exactly on this one. We added, let's say, a small perturbation or approximation. Actually, we focus on the problem where we approximate the zero in the variational inequality with minus epsilon for some positive epsilon. So we approximate the variational inequality, and we try to minimize some criteria among all, let's say, approximate solutions of this variational inequality. Reasons for doing this, I would say at least a few. First of all, when you solve numerically a variational inequality, actually you don't compute the exact solution, you compute an inexact solution. And so in this way, we allow for feasibility of inexact solution of the lower level. But more than this, I would say that the most interesting reason for me is that in this way, we, let's say, by enlarging the feasible region, we add some flexibility in the selection. So rather than sticking to, let's say, the best solution, we may give up, let's say, a little bit of optimality, hoping maybe that you can perform a larger improvement in your objective function. So that again, this flexibility gives you the chance to get much more in your optimization problem, a much more relevant gain. And then the third reason, which you will find out during the talk, is that essentially the introduction of this approximation allows to gain regularity, and this is helpful in computational framework for algorithms. So just to make things even more clear, what happens here when you have, for instance, an optimization, the optimality condition of an optimization problem in the lower level, by introducing this approximation, what you're essentially doing is that you are allowing epsilon minima. Okay, so enlarging the region, you consider minima and epsilon minima in this way. And when you are dealing with, let's say, in the lower level with a Nash game, so that you have players, each of them wishes to maximize its utility, which is supposed to be continuously differentiable and concave, and this set of feasible strategies convex, so that we can rephrase the game into a variational inequality through the gradient of the gain that is given by the operator G here. Then what you actually find is that essentially you are considering some sort of epsilon equilibria in such a way that you consider an epsilon equilibrium when all players are at an epsilon maximum of his utility, which can't be improved by unilaterally changing his own strategies. So somehow this approximation gives us the chance to look for the minimum of our function f over a set of epsilon minima or epsilon equilibria. Then an important thing is that actually this kind of approximation somehow behaves well. So like the title here, Exactness behaves well. Here I have brought three basic results generally from literature. The first one is just stating that you are actually with feasibility in the approximated problem, so means you are allowing approximate solution, you are approximating optimality conditions in such a way. So this V provides a merit for solutions of possible solution to a variational inequality. So it is this quantity is zero if and only if it's a solution of a variational inequality. If you allow for the approximation, then the value of this function is below these thresholds, which depends on epsilon. And moreover, if you consider that your feasible region is a compact polyhedron and the variational inequality as an affine operator, then actually feasible solution of the approximated problem are not even physically far from the solution set of the variational inequality, so that this inequality holds, you have a feasible solution. Its distance from the solution set of the variational inequality is less or equal than this quantity here. And the last property is telling you that actually you have convergence. Even if you want to solve the problem with epsilon equal to zero, somehow you can try to perform it from this approximated problem, since as epsilon goes to zero, if you have a solution, a sequence of solutions of optimal solutions, sorry, for the approximate problem, they behave well, meaning that the cluster points of this kind of sequence is an optimal solution for the exact problem. So that you could use this also as a tool in a computational framework for the exact problem. Oh, I did not say that you need to put some continuity and compactness assumptions that allow you to, let's say, essentially to take in limits. So, but the message is that these inexactness somehow gives you possibility to control it, okay, somehow. And now let me consider the framework in which I will show you some first results. So we suppose that in our problem, we consider to minimize a convex function, which is also continuously differentiable. And we stick to variational inequalities where the operator is affine and monotone over a convex and compact set Y. So this is the framework I'm considering from now till the end of the talk. And one possibility to tackle this kind of problems, a classical approach for semi-infinite program, is to replace all these inequalities by taking the maximum over Y, and this essentially in this equation amounts to replace these with a unique inequality constraint. I also switching the sign in such a way that it becomes a classical less or equal zero constraint, where you take the maximum of all these quantities here. Okay, the problem is exactly equivalent. What you are gaining now is that you have recast our problem into a no-smooth convex optimization problem. Indeed, because this function, which actually amounts to the gap function of let's say almost the gap function of the variational inequality. There is an epsilon term here, which makes a little difference, but not much really, is convex and continuous under our assumption. This is the reason why I stick to affine monotone variational inequalities. So somehow we can now try to exploit tools from no-smooth convex optimization and so from convex analysis and convex optimization. And moreover, this problem here, thanks to the introduction of epsilon, is going to be a good optimization problem in the sense that it satisfies constraint qualification. And this is what I'm going to show you. So let's keep in mind that from now onwards, I will focus on the problem in this format here, okay? Where the constraint is given through a convex function, which since it involves a maximum is likely to be no smooth. And the interesting result is this one, and you need epsilon to be positive so that you actually are approximating. If you reformulate our hierarchical program in this convex format, then it satisfies the so-called standard Mangasarian-Fromovitz constraint qualification, meaning at any point in all the set Y, also a point which are not feasible. What I mean by a standard Mangasarian-Fromovitz constraint qualification, it means that the point, either the constraint is constraining function is negative, so let's say a Slater type condition, or this condition below holds, which somehow amounts almost to some optimality for a feasibility problem. I will be back to it in a moment. So this sounds like optimality condition, and you're saying that if it holds, actually it can hold on. It can hold only if lambda is 0. Okay, this is a way in which you can recast somehow Mangasarian-Fromovitz constraint qualification. And you can prove that this holds at any point x when you have our approximation. Indeed, I skipped this earlier, but under our set of assumptions, the variational inequality has at least one solution. The operator is a fine monotone. We are on a compact, convex and compact set. So we have a solution. And so since we have a solution, the solution therefore satisfies this later condition here, because indeed at the solution, this maximum is 0. And so this becomes exactly minus epsilon. So that for feasible points, we have the classical Mangasarian-Fromovitz constraint qualification. At infeasible points, this condition holds up well, because these actually are the, if lambda is positive, these actually amount to the optimality conditions for a feasibility problem. So for our problem. So it could, an unfeasible solution could satisfy this with lambda positive if and only if the problem is unfeasible. But we know that the problem is feasible, because the solution of the variational inequality is a feasible point. So this this Mangasarian-Fromovitz constraint qualification holds in all of y, feasible and unfeasible points, and this allows us to get to an exact penalization result. So if we move the constraining function into the objective function with a penalty parameter, and we take the positive part here, then what happens is that if the penalty parameter is above some threshold, then this problem is somehow equivalent to our original problem, saying that any optimal solution of the penalized problem is also a solution of our original problem. And this holds because we have the Mangasarian-Fromowitz qualification in and outside the feasible region, okay? And I will briefly tell you that epsilon positive is the essential assumption here. I have an example where exactness fails for epsilon equal to 0, and I just want to minimize a quadratic convex function over the solution set of this very easy variational inequality. The operator is the identity, the feasible region is the unitary hypercube, so that 0 is the unique solution of the variational inequality, and therefore is the solution of the hierarchical program as well. But if you run the computation, you will get that the constraining function has this form, therefore this later is not possible to be satisfied. And indeed, Mangasarian-Fromowitz does not hold at this point. And if you try to check if it solves the penalized problem for some value of rho, you will find out this condition, which at 0 actually read that the coefficient C has to be with non-negative components, and indeed I did choose a different C just to make this not work. So if you have 0, if you have the problem with no approximation, exactness fails, and the failure of exactness does not allow us to try to study, let's say, not study, to design some algorithms through this penalization approach. And actually, well, this is the core of it. And essentially, in an algorithmic framework now, what you can do is exactly the following. You try to solve this problem for some value of the penalty parameter rho, and if it doesn't work, you increase the penalty parameter. And this is what is written essentially in this slide here, where I added some additional features. So at each iteration, I'm trying to solve the problem for a value of the parameter. If I fail, in the sense that the optimal solution is not feasible for the original problem, I increase the penalty parameter and I repeat. What I'm adding here are two features. First of all, I'm not asking to solve problems exactly at optimality. I'm simply satisfied when I get an eta k minimum point at each iteration, and eta k decreases with as iterations go by. So I'm asking for more and more precision as time as iteration go by. And also I allow the possibility whether to check not exact optimality, but to check whether an infeasibility is above some threshold beta here, okay? And well, if you want, you can take eta k equals 0 and you have minima. You can take beta equal 0, and here you are actually checking feasibility. And clearly the suitable tool for performing the minimization at step 2 is clearly we are dealing with a no smooth convex optimization. So one possibility is using a projected subgradient method, and I performed it here for you. I just this is just computing a subgradient. Okay, these steps here, these beta I are giving nothing else than a subgradient of the function. You need to compute a maximizer yi of the constraining function here, and then you perform the step. And we know that if we choose this step side alpha I in a suitable way, then we have that cluster points of this sequence are minimizer. And moreover, we can control the distance from the optimal value, meaning that we can actually perform this computation of approximate minima here. There is another way I can run it through, but I'm skipping it because I'm a bit late. And here I can give you a first convergence theorem. Actually, point A is nothing else than exact penalization, because it says that if I run exact minima and then I choose beta to be 0, then I find the optimal solution in a finite number of iterations. But this is exactly saying that if the penalty parameter is large enough, the solution of the penalized problem is a solution of my problem. What is interesting is if I'm allowing some positive threshold for feasibility. Indeed, when you try to compute things numerically, there are always some uncertainties in the values. So if you allow a positive threshold, then you don't need to suppose exactness, and then you still have this convergence result that says that the cluster points of the sequence that you generate satisfy these two conditions. So the value of the constraining function is below some beta, and the value at x bar at the cluster point is less or equal than the optimal value, meaning that if x bar is feasible, so actually it's this value is less or equal than 0 and not only beta, then you have found out an optimal solution. Then, well, actually, we could run also a proximal type version of this. I will put you the slide here, and without giving the details, rather than doing a projected a subgradient method, we can try to perform a proximal step at each iteration, which is defined here, and we can prove convergence here as well. So this is what I wanted to tell you. I repeat it, it's just preliminary. We have a first paper on this. And well, allow me 30 more seconds for a short commercial. You know that Europe is the group inside the Euro for Continuous Optimization. I've been honored to chair it for a couple of years now. We were supposed to have a meeting this July in Toulouse. It is no news, no unexpected news to everyone that it will be called off. Actually, it will be called off, I think, today by the organizers, and we are planning to postpone it to next year. And in this meeting, I organized a stream on the argument, on the topics of this workshop as well, together with Matthias Studigl and the European Network for Game Theory, GameNet. So we are trying to repropose it next year, and I hope you can join. We had 30 talks scheduled for this year. So let's say this is the first announcement that we are trying to reschedule our next meeting. So this is it. Thank you.
Thank you,
Sorry.
Giancarlo. Yeah, so.
More than I expected.
Yes, so here is a first question for you. You can also check the chat. So Lacra, any ideas on extending to non-affine G?
Well, this would be a next step. The thing here is the following. I'm going back here. You look, if your risk is to lose convexity here in the reformulation. So probably we should look for some different way to approach this problem when G is not affine, because here you are likely to lose convexity. Clearly, everything I said is still true if the function G at x times x is convex. Okay, everything remains the same, even if you are not in an affine situation, but you need to have that to have convexity here. Otherwise, we should probably go towards some other direction with, because this amounts to something which won't be convex. So probably you need to do some sort of convexification and go in some, let's say, less clean way.
Thank you.
Oh, Giancarlo, I have a quick question also. So your epsilon is fixed from the very beginning, right?
The parameter.
Yeah, the epsilon. So
Yeah.
I was wondering, would it make sense if instead of epsilon it was some sigma times the square norm of x minus y? You see what I mean?
A different kind.
So it would be a very specific epsilon that depends on x and y. Would that make any sense? Or?
Yeah, yeah, I think it would make sense. Actually, I was thinking that you were going to ask to take. Yeah, it would. I think it would. Yeah, it's and I think there are even more results that can be exploited. Yeah.
Okay, so then in this case you can use you can move to non-convex cases probably, because that would be some normal cone of a non-convex set. Or I don't know.
Okay, thank you.
Just throwing an idea.
Thank you for the good suggestion.
Okay.